welcome to everyone. Good morning, good afternoon, good night, wherever you are in the world. I'm very delighted to see that you are interested in this webinar. Maybe some words about myself. I've been working in the International Electrotechnical Commission, working on the development of standards for the last more than 20 years, and I am the convener of Working Group 31, which is responsible for the IE classification that we will discuss a little bit later on. Since 2 years, I'm also the chairman of the Technical Committee 2. So what I want to do with you today is, first, I would like to give you a detailed overview and description of the relevant standards for classification of energy efficiency of motors, of power electronics and motor-driven systems. And then, of course, I will give you also some ideas on how to test the efficiency, what are the testing standards, and I will give you updates on the latest status of all of these standards. So let's dig right into the topic with this overview, and we'll go through this line by line. As you can see, I've made 2 columns here. The efficiency testing standards are in this column, and the efficiency classification standards are in this column here. In the first line, the standards are about the motor, and this is particularly motors that are designed for online operation, that is, motors that are designed for 50 or 60 cycle grid operation. When we want to test these motors regarding their losses and then calculate the efficiency, what we need to look at is the IEC 34-2-1 standard. This standard has been prepared in the Technical Committee 2, Working Group 28, and you can see that 3 years ago the latest edition, which is number 2, has been released. So this is a quite mature standard, and currently no significant updates are planned. The classification is contained in the 34-30-1 standard, which was developed in Working Group 31. This is the first edition. Actually, this is also a rather mature standard. It is the successor of the 34-30 standard, which was available for quite some time now. We'll go a little bit into the details, what's included in these testing standards and efficiency classification standards later on. And the second line, that's about motors that are operated on variable frequency drives, that is, motors that are operated not on the grid, but on variable frequency, variable voltage. Here we are working on a new edition of the efficiency testing standard 34-2-3. The first edition is a few years old and is only covering induction machines, no other types of motors. The new edition that's currently in the making will also include synchronous machines, and it will also include efficiency interpolation procedures. Again, a little bit more details later on. The second edition has been, or the first committee draft for the second edition has been released just a few weeks ago. The efficiency classification on motors that are operated on variable speed drives is contained in 34-30-2, and here a little over 1 year ago we finished the first edition, so this is also mature and not being developed any further right now because it's in a good situation. When we look at variable frequency drives, that is power electronics, and motor-driven systems, that is power electronics plus motor, there is the standard IEC 61800-9-2. This is not prepared by IEC TC2, but rather by the subcommittee 22G, and there in particular by Working Group 18. This standard has been published in its first edition about 1 year ago, and this first edition was effectively an editorial overhaul of the European standard that had been there before. We are not totally happy and satisfied with this new edition, so a second edition of this standard is already in preparation. That's mostly what is available in IEC for end users. We do have a rather generic standard, which is the -9-1 for extended products. Extended product means the combination of power electronics plus motor plus an application, either fan, pump, or compressor, or whatever. But again, this is a rather generic standard. It's more aimed at people that write standards and not so much aimed at end users, so I will not cover this here in the webinar. Oh, I'm sorry, that was the wrong key. Now I clicked the wrong button, I'm sorry.
No problem, Martin. Let me recover the control.
I wanted to turn off the pointer and pressed 1 centimeter too far to the right. Can you turn it on, Fernando? Sorry.
Yes. So 1 moment. Yeah, I need to. Yeah, so 1 moment, please.
Yeah, everything's good.
So let me presenter again. That's
yeah.
it. Normally it should work again.
It's good.
Okay.
Everything's working again.
Okay.
Thank you. So we have another project that's currently undergoing, and that is an efficiency guide. That's the 34, let me press the right one now. That's the 34-31 standard. We do have a very, very, very old edition of that. It's actually a technical specification and not a standard. But the old edition is needs to be revised due to the new developments, and the very first committee draft is expected in the next coming weeks. So this is effectively a guideline to the philosophy and the ideas behind all the other standards that are listed here on this page. I highly recommend reading this as soon as it is released, which should hopefully happen by the end of this year. Now let me first go a little bit into the applications on just 3-4 slides and give you a generic explanation on why and how you can save energy by reducing the speed, or in other words, how variable speed drives save energy. And we will first look at square torque applications, that is pumps, fans, and compressors, very generic. And then in the second step, we will look at constant torque applications, mainly conveyor belts. So let's assume we have a pump, a heating pump, or a water, let's say it's a heating pump in a building, so it's a closed circuit, pumps the hot water in a closed circuit, and this here is the system curve. The red curve here, that's the system curve. If you're not familiar with this kind of graphs, what we have here on the horizontal axis is the flow rate, so basically the amount of cubic meters of fluid that is pumped per hour. On the vertical axis we have the pressure that is required to do that. And the power that the motor has to develop, disregarding efficiencies and everything, the power that the motor has to develop is given just by the pressure and the flow rate. So let's assume operating point number 1 is the full operating, full pressure, full speed of the motor, and we've got the flow rate of Q1. If we want to reduce our flow rate, for example, over the daytime, or because it's very hot and the heating system doesn't have to operate any further at full power, and let's say we want to go from flow rate Q1 to the flow rate Q2, there are effectively 2 options what we can do. The first option is we can close a valve and we can throttle the system. Then the system curve will change its shape and will go to this curve here. So we continue to operate our motor at full speed. This is the motor curve, the pump curve for full speed, but we change the system curve by throttling, and we arrive at operating point 2. Here at operating point 2, we get the desired reduced flow rate, Q2. However, we need full power because if you look at the power equation, we have reduced the flow rate, so Q is going down, but at the same time we have increased the pressure because we've closed a valve. So delta P is going up, so the power that we need here in operating point 2 is more or less the same as the power that we needed in operating point 1. But we're pumping much less fluid, so the efficiency drops considerably. We're wasting a lot of energy. That can be improved by not closing a valve, but instead reducing the speed of the pump. In that case, we remain on the original unthrottled system curve, but we now change the pump curve from the curve that is there for the original speed to, let's say, 80% pump curve. And we arrive at operating point 3. Operating point 3 has the same flow rate as operating point 2, but this time the pressure is much lower, which means that the power that is required is much lower, meaning that the efficiency here in operating point 2 is dramatically better. So, long story short, we can save a lot of energy in this system when we have to reduce the flow rate and when we do this by reducing speed, variable speed drives instead of throttling. This is the ideal case, you could say. Now, it doesn't always work as nicely as is presented here. Let's assume this case, and this is now an open circuit. Open circuit means that you have a system that spills, for example, water out of a hose. For example, a fire water pump would be an open circuit. For open circuits, you have the so-called static head. That means you have a certain amount of pressure that is simply needed to pump the water upwards to the point where it is released. And you can see here, when we reduce the operating point or the flow rate from Q1 to Q2, the gain by using a lower speed instead of throttling is much lower, simply because we have this static head. But still, there is a lot of saving potential. It's not as big as before, but still there. Now we go to first let me show you another example. This could be a water pump in a big house, in a big office building, in a block of flats, an apartment flats. Very often you have a situation where one pump is not enough and you have a multiple number of pumps. In this example here, you got 3 pumps. And in a typical scenario, in such a situation, you would use one of the pumps with variable speed control, and the other 2 are just on-off, and you turn them on when you need them and turn them off when you don't need them. That would be the most efficient and also the most cost-effective way to operate these pumps. Now let's go to conveyor belts. And in our first example of a conveyor drive, we have this typical mass conveyor here that's just conveying dirt or stones or whatever upwards. And the diagram that describes this conveyor belt is very similar to the diagram that we had before for the pump, fan, compressor, except that on the horizontal axis here we got the transport speed. On the vertical axis we've got the force or the drag. And again, power is given by the multiplication by the product of transport speed and drag. Same situation as before. Let's assume we have our conveyor fully loaded. Then we're in operating point 1. We need a certain speed and we need a certain drag to get the mass transported. And now let's assume that we want to transport only half the mass. So the lorry or whoever pushes or puts the mass here on the belt is reducing the amount of mass to the half. We have 2 options. The first option is we continue to operate the conveyor at the same speed. However, because there's only half the mass pulled or pushed onto the belt, the force and the drag reduces to half. So we arrive at operating point 2. The other option is we could reduce the speed of the conveyor. So we go from V1 to V2. But as the conveyor then will only operate at half its original speed, the mass that is flowing onto the converter will fill it up entirely, so the drag is not going to change, and we arrive at operating point 3. Now, it is remarkable to see that both operating points, 2 and 3, are at the same power curve. So regardless of if we reduce the speed or if we just, this is reducing the speed, or if we just halven the mass flow and reduce the force, we arrive at the same output power, we arrive at the same efficiency. So in this case, variable speed control is not going to help at all. It's not going to change anything. In reality, you always have a combination of the force, the drag that is needed to transport the mass or the system and the force that is needed to overcome the friction that is included in the system. And if the friction has a significant part in the total drag that is required, we're getting again to a situation where speed control, here operating point 3, reducing the flow by speed control is more energy efficient than reducing the flow just by reducing the torque. So the more friction the system has, the better the speed control is going to give you energy efficiency, or the more energy efficiency you're going to get by speed controlling. Long story short, if you have an application, you will need to calculate the efficiency savings that you can achieve by variable speed control. And in order to do that, you will need to know the losses in a number of operating points meaning speed and torque. And for that reason, the standards that we have developed give you all the necessary information, and I will come to that a little bit later on. Here's a summary of what I've just said. We have fans, the energy saving potential is very high. We have, by speed control, we have pumps, screw compressors, piston compressors. The energy savings potential is also high, depending on how much friction you have, more or less. And we have all the conveyors, hoist drives, moving walkways, stairways, and so on. And then the energy saving potential by variable speed drives is not so high. You may end up, in rare cases, however, you may end up in a situation where a variable speed drive, speed control, could even increase the energy consumption due to the additional losses that are given by the power electronics. This is one factor, variable speed control. Of course, you can only save energy as long as you reduce the output power and as long as you have a situation where you don't need full power. Then the second, let's say, building block to save energy are energy efficient motors. They always improve energy efficiency as long as you don't have dynamic operation. When you have dynamic operation, energy efficient motors are not good. We'll come to that later on. And of course, as long as the turn-on time, the operating time is long enough. If you only operate the motor for a few minutes per day, energy efficient motors will be counterproductive. Now, let's go into the standards. And we'll start with the classification standards, of which we have two different ones, the 30-1 and the 30-2. First, you need to understand which motor falls under which classification standard. And the most important thing to remember is that each and every motor falls under one of these two standards, but never ever under both. So it's either or. It's either this one or that one, never both. Which one it is depending on the rating of the motor, obviously. If the motor is rated for grid operation, that means operating on a fixed 50 or 60 cycle per second grid, then it's always 30-1. If the motor is rated for both grid and frequency converter operation, which is actually true for most induction machines on the market, then again it's 30-1. If the motor is rated for frequency converter only and not for grid operation, then it is 30-2. So most standard motors, most induction motors are 30-1. And it doesn't matter if they're operated on the grid or if they're later in the application operated on a frequency converter, they're still under 30-1. Also line start permanent magnet motors, which are rated for grid operation, fall under 30-1. Motors for 30-2 are mostly synchronous reluctance motors, permanent magnet synchronous reluctance motors, and also some very few induction motors in case they are designed for frequency converter operation only. But this is very, very exceptional. There are very few cases of that. If you look at the market, and that's only an estimation, of course, I would estimate, to give you a rough idea, that probably 60% of the machines, of the motors, are still operated directly online. Probably 30% something are operated on a frequency converter, but are still rated for online operation. So this is probably 90% of the market or maybe even more, and this is all under 30-1. Then we have high dynamic applications, the so-called servo motors or servo drives. They are not classified regarding the energy efficiency for very good reasons. The reasons being that these motors must be very quick in acceleration, very quick in deceleration, so they need to have a very small rotor. And a lot of the energy consumption comes from acceleration and deceleration. It wouldn't be useful at all to oversize these machines to get a better energy efficiency in continuous operation. So they're not applicable. And then the motors that are really rated for 30-2 are very small. Basically, it's unconventional technologies. New motors, that was the idea when we created that standard. We wanted to have an equal level playing field where all the motors could be compared and all the motors could be given and rated in an efficiency label. That was the basic idea here. You see the efficiency labels 1, 2, 3, 4 that we have for the grid-rated motors, and 1, 2, 3, 4, 5, the new one, 5, that is here reserved for the motors that are for frequency converters only, so to speak, the new motor technologies. Speaking of new motors and comparing high efficiency with low efficiency motors, you sometimes hear some discussions, oh, high efficiency motors are going to be very big, they're going to be very costly, they're going to be very heavy, you're going to need a lot of energy to build these motors, and it's not useful to use high efficiency motors because you have to use such a high amount of energy to create them. And of course, depending on the technology, this can be very true. If you, for example, build IE4 induction machines, they are much heavier, much larger, much bigger than IE2 induction machines. But this is not the end of the story. There is new motor technologies on the market already available from different manufacturers, and you see some examples here from a very well-known company, ABB. And this picture, I like this picture a lot because it shows you a traditional IE2 motor, which is an induction motor, and it shows you one of the new motor developments, the synchronous reluctance motor, which is IE4, and you can see that both motors from the outside are exactly the same. They have the same size, the same volume, the same weight. I don't know about the price. You've got to ask ABB or one of the many other suppliers. These motors are now available from several suppliers. ABB is just one example. You've got to ask them about the price, but I wouldn't see any reason why these should be significantly more expensive than those. Actually, they should be a little bit cheaper. You will need a frequency converter to operate this motor. That's the drawback. You will need a frequency converter. So if you are planning on benefiting from variable speed drives, this is the perfect motor for you. And it has 40% less losses. And with our new standard, the 30-2, we can now classify these machines just like we can classify those machines. Again, 30-2 is not for servo motors, not for servo applications where we have frequent overloading, field weakening operations, speed torque changes, no thermal steady state, and so on and so forth. These motors are really, really different. Here are some typical applications that are covered by the 30-2 standard: belt conveyors, roller conveyors, pumps, compressors, fans. You see some images here. And then here are some typical applications that are not covered because they are high dynamic, because they are short time duty, like this robot drive, like this hoist drive here, pick and place machines, machine tools, rack feeders, and so on and so forth. These are not covered. How do you get the nominal efficiency for the rating of the efficiency classes? We have efficiency tables, i.e. 1, 2, 3, 4, for grid-operated motors that are in 34-30-1. For the 30-2, we took the same tables. Actually, we took the 50 cycles tables. There are also 60 Hertz tables available, which we didn't use. And we added a new table, IE5, which is exclusively for new motor technologies. Then, as we can only operate these machines here according to 30-2, we can only operate them on frequency converters, we have set one operating point. And that one operating point is at 100% torque and 90% speed. We have discussed a lot, should we not use a number of different operating points and build a scenario, build an average, whatever. The problem is, whichever torque and speed points we choose and whichever scenario we build, it's not really relevant for all applications. The applications that we find in the industry are so various that it would be very difficult for us to set just one, let's say, scenario where we could find an average. So we said, okay, we just look at one point only, and this is only for the rating, of course. So this is a comparable point where we can compare the efficiency of these variable speed motors with the efficiency of the grid-operated motors. Why have we chosen 90% speed and not 100% speed? The reason is that ideally the voltage of the frequency converter should be equal to or should be changed in the ratio of speed and frequency. But the frequency converter itself has a voltage drop across the IGBTs, across the electronic switches. And so the output voltage of a frequency converter is always a little bit lower than the input voltage. And if we had written here 100% speed, we would not have had the voltage that's required for full magnetic flux at 100% speed. And so to cover that, we've discussed this a lot with the frequency converter experts in subcommittee 22. And we finally decided that we would use the 90% speed point. And that 90% speed point will allow us to get full magnetic flux even at a reduced voltage, and it is harmonized across all the standards that I've shown you up front, even the 61800-9 series of standards. Everyone uses now this 90% speed point. Another thing that needs to be done, we have additional losses in the motor due to the switching of the voltage by the frequency converter. And these additional losses must be compensated. Otherwise, the results wouldn't be comparable to the motors that are tested on the grid. And we do this by introducing an allowance factor, this RHL factor, and the nominal efficiency that the motor must meet is calculated from the efficiency that you get from the tables I1, 2, 3, 4, 5. These are the same tables that you also find for the grid motors. And then you apply this little formula and reduce the, or increase the losses, reduce the efficiency by this RHL factor. The smaller factor is for the smaller motors and the larger factor is for the larger motors, because at the smaller motor we ask for a switching frequency that is higher than for the larger motors. Here's a lower switching frequency, so the losses in the motor are higher. And that's effectively it, and so the manufacturer can then calculate the efficiency, the nominal efficiency value, do the testing, and compare his results against the nominal efficiency for the classification. Here are some graphs. It's always nice to see some graphs of the levels that are required. Here on the horizontal axis you got the nominal output power of the motor. Here you've got the typical suspects. This is the IE1, IE2, IE3, IE4, and IE5 nominal efficiency, the nominal efficiency limit. And this is given for motors that are rated for a speed somewhere between 1200 and 1800 RPM. I should say that in the 30-1, where we talk about grid-operated motors, we make a difference regarding the efficiency classification, difference depending on the number of poles. Here, where we talk about, in the 30-2, we talk about frequency converter motors. The pole number doesn't have any meaning, because you can use any frequency and then operate the machine at any pole number at any speed, and we just look at the nominal speed instead of the nominal number of poles. I have also plotted the same curves for different torques across the speed range, which is a rather interesting view. that you probably haven't seen before, and I will not go into all the details. It's just the same values. They're just separated or sorted in another way and plotted in another way. The baseline of this graph is this all works out quite nicely, and the graphs you see here have a physical meaning and they're physically useful and sensible. It's not nonsense that you get from plotting the torque nominal efficiency limits over the speed curve. This is the or a graph that gives you an indication of how many kilowatts you can save by going from one efficiency classification to the next one. This is, for example, for 75 kilowatt motors, how much kilowatt you can save by changing the efficiency class from IE1 to IE2. It would be a little over 1 kilowatt that you can save. If you go further to IE3, the savings would go close to 2 kilowatts. If you go further to IE4, the savings would be around 2.4 or 2.6, 2.7 kilowatts. And if you go further from IE1 all the way to IE5, the savings would be around 3.4 kilowatts for this 75 kilowatt motor. The good question is always, will there be an IE6, will there be an IE7, IE8, IE whatever? I hope not, honestly, because what you can see in this graph that the savings are getting smaller and smaller the higher the efficiency class increases. What we need to do from a standpoint of a regulator, we need to have an efficiency class at the top end that is open for new technologies, so to stimulate the market to move towards new technologies, to move towards motor designs and towards losses and efficiencies that cannot be reached with the conventional technologies. So IE5, we believe, is doing this rather nicely. IE5 is today at least reserved for such new technologies, and we will not have to go any further as long as it's good enough for new motor technologies, IE5. So that was one part, how to do the classification. The second part, as I said in the beginning, as an end user, if you want to know the losses and the efficiency and the gain that you can achieve by using variable speed drives and by using high efficiency motors, you need to know the losses and efficiency in a number of different operating points that are given by your application. And that is exactly what we will provide you with the interpolation procedure that is included in the 34-2-3, or rather will be included in 34-2-3 when the new edition becomes available later this year. What we have there is an interpolation formula for losses. So effectively, what you need to know is these 7 coefficients, CL1, CL2, all the way up to CL7. And these coefficients will be provided to you by the motor manufacturers. And already now, as we speak, a number of manufacturers are working on these tables. When you have these numbers, what you also need to know is the speed and the torque for which you want to know the losses. And these numbers here, speed and torque, are always relative numbers. So at standstill, no load, N will be 0, torque will be 0. And at full speed, whatever that is, at full rated speed, N will become 1. And at full torque, whatever the rated torque is, T will become 1. So if you enter N equal to 1 and T equal to 1 into this equation, you will get the losses for the full speed and full torque. And the losses will also be relative to the total losses. I'm sorry, to the total power, to the rated power. How do you obtain those coefficients? Well, in an ideal world, you would get the coefficients from the motor manufacturer and you don't have to worry about anything. If the manufacturer doesn't give you the 7 coefficients, what at least he should provide are the losses in these standardized 7 operating points. So here we have the relative speed from 0 to full speed, 100%. On the vertical axis, we have the relative torque from 0 to full torque, 100%. As I said before, the rating and the classification of the machine is done at a full torque, 90% speed. So that point number 1 would be the rating point where we determine the efficiency and losses for the classification. And the motor manufacturer should give you the losses in this operating point. It should also give you the losses in these other operating points, 1, 2, 3, 4, 5, 6, and 7. And when you have the losses in all these operating points, what you need to do is you have to enter the losses in these 7 simple formulas. They look complicated, but they're not actually complicated. This is just a one-time experience that you have to program this into Excel. And also we will provide you with all this, these formulas in a spreadsheet that will be available from the IEC website, so actually you don't have to do anything. Just enter the losses that are provided by the manufacturer in these 7 operating points, and then you get the coefficients, CL1 to CL7. Unfortunately, not all of these coefficients are harmonized. With 61800-9-2, we're still working on that topic. You can also see that these operating points, the operating points are not harmonized. The coefficients are harmonized. The operating points are not. You can also see that the operating points are designed so that they cover different types of applications. Here we've got a continuous torque application at full torque. That could be a conveyor belt or a hoist. Here we've got the same for 50% and for 25% torque. And if you have a pump or a fan, then these points here become interesting, 7, 5, and 1. Or if it's at a little bit lower torque, the points number 6 and 4 are interesting for a fan or a compressor application. This is another way how a manufacturer can create the 7 coefficients, provided that he has done more testing and provided there are more operating points available than just the red 7. If there are more points, typically these 16 points, there's also the opportunity or the possibility to do a numerical search for a minimum. This again will be included in the Excel sheet. It's nothing that an end user would have to worry about. Let me take the last few minutes that we have available and guide you through some flowcharts on how to determine, on how to use the different energy efficiency standards for the different types of applications, for the electric motor, for the frequency converter, the driven equipment, the power drive system, and so on and so forth. And we will start with the electric motor. The first question that you should ask is it rated for variable speed operation? If the answer is yes, and you're a manufacturer, then you have to provide the 7 variable speed load points according to 34-2-3, or even better, the 7 interpolation coefficients. That will enable the end user to determine the losses in all other operating points. This is true for all types of variable speed motors, regardless if they are rated for grid operation also or only for variable speed. The next question is, what is the rating of that motor? Is it rated for grid operation, or is it rated both for grid and variable frequency operation? If the answer is yes, then the classification is according to 34-1. If the answer is no, that means that the motor is rated only for frequency converter variable speed operation, then it is covered by 34-30-2. And of course, the next question is then, is it in the scope? If it's not, then there is no labeling. Here again, if it's not in the scope, there is no labeling. And if it's in the scope, then you have the testing standards 34-2-1 in case of motors rated for grid operation, 34-2-3 in case of motors rated for variable frequency operation only. And then after the testing, you can do the classification and assign an IE class to the motor. For frequency converters, the situation is similar. The classification is contained in the 61800-9-2. Again, you've got to determine losses. In this case, there are 8 operating points. And again, the standard contains interpolation procedures so that the end user is able to determine the losses in all operating points when he knows these 8 values, just to evaluate their application and the losses and the efficiency in their application. And then, just like a motor, the efficiency of a frequency converter is determined at 90% frequency in full load. And then there's a little bit different philosophy here with a reference CDM, and you can then classify the frequency converter and its losses into the classes IE1, IE2, or IE0. The power drive system, also contained in 61800-9-2, consists of a frequency converter, variable speed drive, and an electric motor. Here the question is, what type of frequency converter do you have as a manufacturer? Do you have your specific frequency converter or just a generic one? You can use the reference converter if you don't have a specific converter. Do you have a specific motor or just a reference generic motor from the standard? Then you determine the losses and the 8 operating points, and then you supply this information to your customers so that the customers are able to determine the losses in each and every operating point by interpolation. And again, for the system there is a classification. The only difference is components are classified according to IE numbers, IE 0, 1, 2, 3, 4, whatever, and systems are classified according to IES. S obviously meaning system, so we've got an IES 0, IES 1, and IES 2. Driven equipment, there is currently nothing for driven equipment like a belt drive or a gear, as far as I know. And then there are some standards for extended products, namely for pumps, which is a European standard from ISO, for lifts, elevators, escalators, moving walkways, which is also an ISO, or this is an EN standard, this is an ISO standard. There's also a standard for fans, as I've learned, which is not contained here on this graph, but this is then specific to the application. One final information, which is always creating confusion. We have a difference between rules and regulations that are made by lawmakers, like EU directives, EU regulations, or Department of Energy rules in the United States, or other national legislation in India, in China, in Japan, in Brazil, wherever. These regulations, directives, rules, whatever, are legally binding. You have to follow these, or otherwise you're breaking the law in these countries. This goes both for the manufacturer and also for the end user, basically for everyone. On the other hand, we're talking about standards, national or international standards from the International Electrotechnical Commission, from the ISO, the European standards, North American Motor Manufacturer Association, and many, 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 many others. These standards are basically for information purposes. They are not legally binding. If you ignore these standards, you're normally not breaking the law. However, it may be that standards like these are referenced in a legal text. Then, of course, the standard has to be followed as well. It may be that the manufacturer is referencing the standard in his product documentation. Then, of course, he has to follow the standard, or otherwise he's breaking the law as well. Customer orders may be according to standards. And there may be marketing agreements, for example, the Lima Premium label that is also referring to a certain standard, and all the manufacturers that have signed the agreement must then be following the standard. Finally, what's also interesting, standards have often normative parts and have informative parts. Standards can be real standards, or they can be technical specifications or technical reports. And again, only the normative part of a standard must be followed under these circumstances here. The informative parts can be ignored, technical specifications can be ignored, technical reports. All of these may be ignored if you so wish, but if you ignore them and then later have a safety problem, for example, then you will have a hard time explaining the judge why you ignored the standard. But it's not breaking the law. So, thank you very much. this is what I wanted to tell you, and now I will give the microphone back to Fernando to moderate the question and answers session.